This is the first lesson for Module 7, The Nature of Light, for the HSC Physics course, Maxwell's contributions to electromagnetism. Every time I teach this, I get the same thrill. I find it absolutely amazing that a man in the 1860s was able to show that electricity and magnetism are unified through light, through the speed of light. It's mathematically quite beautiful, in my opinion. The maths itself is kept out of the HSC syllabus for obvious reasons. It can get quite complicated. So I will stress from now that I will be including maths equations in this lesson, but they're not examinable under any circumstance in the HSC itself. Okay, they're just there for those who are mathematically inclined, just to give you a bit of context as well. So before I talk about Maxwell, let's go back to 1854. English scientist Michael Faraday, world-renowned for his work on electromagnetism, electricity and magnetism, and for inventing the electric motor. He invented the first electric motor, and for also work in electrochemistry, so work involving batteries. So he experimentally explored electromagnetism. He didn't have any theoretical background at all, didn't have any formal training at university. He basically used magnets, coils, solenoids, voltmeters, ammeters for his measurements. And he introduced the idea of lines of force to explain the effects of magnetic interactions. Okay, for example, two bar magnets. Suppose you bring them close together, okay, of the same like polarity, in this case south-south, so they will repel, right? Drawing isn't really accurate, but anyway, get the idea. So he believed that there was some force acting between magnets, for example. And he also believed that there was, suppose you have a current carrying wire, I'll denote current with I. He believed that there was this force field radiating outward from a current carrying wire that somehow would affect a compass nearby, compass needle. This was actually shown by Hans Christian Ørsted in the year 1820. And then came along in the 1860s a Scottish mathematical physicist named James Clerk Maxwell. This is a guy you should know for the HSC. Okay, Michael Faraday as well. Should be familiar with him from Module 6. So James Clerk Maxwell theoretically developed what's called classical electromagnetism. Okay, the theory of classical electromagnetism, originally involving 20 equations connecting electric and magnetic fields using the known fundamental laws of electricity and magnetism at the time. So he replaced Faraday's lines of force with electric and magnetic fields. Being a bit sloppy here because I want to save some space and time. So E with an arrow on top and B with an arrow on top. Okay, so the arrows represent vectors. E for electric field and B for magnetic field. So a field by definition is an entity with a value at every point in space. Okay, it's like a three-dimensional web. So for example, a magnetic field exists around a bar magnet. Okay, it goes out from the north and into the south. Right? And you can picture this in 3D, in three dimensions. I'm constricted here to one dimension because of the device that I'm using. And also an electric field exists around a charged particle. Okay, that was known at the time as well. And so I'm now going to introduce Maxwell's four equations. Okay, these are known as Maxwell's equations. Remember, these were originally 20 of them, but they were reduced to just 4, okay, because of things like symmetry and whatnot. So I'll start with the first Maxwell equation. It's known as Gauss's law. Okay, named after Carl Friedrich Gauss, a German guy. Gauss's law for electricity. It's a very simple statement. It basically says that there are objects called charges. okay, which make or absorb electric fields. It's very simple. Where you're taught this in junior science. Okay, suppose you have a positive charge, you've got electric field lines coming out of it, right? Perpendicular to the surface of the charge, right? E with an arrow on top. Negative charges, they eat electric fields. Okay, the field lines, once again, perpendicular. I haven't drawn it well, but anyway. So there are two types of charges in nature, positive charges and negative charges, according to Gauss's law for electricity, and they make and absorb electric fields. Now, for the mathematically inclined, this is what Gauss's law for electricity looks like. I'm going to use integral form. I'll be taking these equations with me to the grave. In fact, every physics or engineering student can't get their degree without memorizing these equations. So this is basically telling us that suppose you have some sort of surface, okay, and you've got charges, Q. Okay, these points are charges, Q. And suppose you take some element of that surface, some small area, let's call it dA, okay, represented by a vector, normal to the surface. Basically tells us that if you sum over all the charges, right, Q, okay, where this symbol here, epsilon naught, is called the permittivity of free space, just a number, basically. That tells you the how easily an electric field can pass through vacuum. It's a very small number. 8.85 times 10 to the minus 12. No, I'm going to leave the units out because it's just a number. It's on your HSC data sheet. You don't need to memorize it. So suppose you sum over this, sum over all the charges for some surface, you will find there's an electric field that exists there. Okay, in other words, you can say it another way. If you sum over this surface here, over this entire area, the electric field contributions, that's due to charges Q existing on that surface. Maxwell's second equation is Gauss's law for magnetism. It basically says quite simply that magnetic field lines travel in loops. They always travel in loops. In other words, magnetic monopoles don't exist. At least not yet. We haven't discovered them in nature. Okay, quite simply, this can be illustrated using a bar magnet, north-south. If you cut a bar magnet in half, you'll still get a north and south. Keep doing so, you'll still get a north and south. Okay? Magnetic field lines travel in loops. They go from north to south, quite simply. And mathematically, it looks like this. Once again, I'll be using integral notation. In other words, if you put a surface, some surface with area A, surface area A, on top of this bar magnet, you'll find that there won't be any field lines coming out on their own. They'll be looping around. Okay, that's what that's saying. So summing over the surface, the magnetic field lines, you'll find that there won't be any individual lines. It's zero. Maxwell's third equation is called the modified Ampere's law, named after André Ampère, French physicist and mathematician, okay, whose surname is now attributed to electric current. So current is measured in amperes. Now, this is where one of Maxwell's breakthroughs came from. Okay, when he realized that Faraday's law of electromagnetic induction, and I'll talk about that next, can work in reverse too. Basically, a changing electric field can induce a magnetic field. So modified Ampere's law states that a current I can induce a changing magnetic field. In addition, a changing electric field can induce a magnetic field. Okay, so from Ampere, we know that if you have a current carrying wire, current flowing to the right, you'll have a magnetic field around the wire. This is from module 6 on electromagnetism. Okay, this is well known. But also Maxwell said, hang on, because Faraday's law of electromagnetic induction states that a changing magnetic flux induces a changing electric field, why not the reverse? Okay, and he used the idea of symmetry in his mathematics quite beautifully. This is the modified Ampere's law. Okay, so a current I can induce a magnetic field. In addition, that's what the plus means, a changing electric field can induce a magnetic field. And this symbol here is called mu, mu naught, it's Greek. This is known as the permeability of free space. A very small number. It's basically a measure of the ability of a material to form a magnetic field. And it's expressed as 4 pi times 10 to the minus 7 on the HSC datasheet. And so, yeah, quite an equation there. But it simply tells you that I becomes B and E becomes B, to sum up basically. The fourth and final equation, final Maxwell equation, Faraday's law of EM induction. This was covered in module 6, which is great. So it should be a recap, hopefully. It states that a changing magnetic flux induces a changing electric field, which in turn induces an EMF, an electromotive force, which is basically voltage. So from module 6, it's expressed as follows. Let's take n to be 1 for now. So epsilon here is the electromotive force measured in volts. Delta phi, that's the changing magnetic flux. And delta t, that's the change in time. In integral form, it's expressed like this. And I should emphasize as well that the L here signifies length, okay, across a loop or a line. Okay, so a changing magnetic flux given by this over time induces a changing electric field denoted by E. Okay, remember, so if you have a magnet, there's relative motion between a magnet and a coil, it's attached to a voltmeter, you will get an output voltage simply due to the relative motion between the magnet and the coil. And the faster, the greater the speed of motion of the magnet coming in and out of the coil, the higher the voltage reading. So they're Maxwell's 4 equations. And the other breakthrough that came about was when, so using those 4 equations, Maxwell was able to derive this, he arrived at this conclusion. When he had this expression at the very end of his calculations, he got out this number roughly. I'm running up here. That's the speed of light, right? So these 2 quantities, the mu naught concerns B fields and the epsilon naught concerns electric fields. These are connected through the speed of light. Amazingly, so light is an electromagnetic wave. That was Maxwell's conclusion. He had solid evidence now. So Faraday hypothesized this. He had a theory, and it was met with quite a lot of resistance back in the day because he had no theoretical proof, no solid foundation, no framework. But Maxwell came along and showed that yes, you were right, light is an electromagnetic wave. And for that matter, all electromagnetic waves travel at the speed of light. Okay, I should denote it with C. So C is celeritus in Latin, it means swift. It's used in physics to denote the speed of light, which is roughly 300 million meters per second. So hence electricity and magnetism are unified through the speed of light, C. And so how do you get electromagnetic waves? Well, you can have a charge and shake it about, oscillate it about a particular axis, an oscillating charge. That oscillating charge will produce an electromagnetic wave. I'll use different colors here. So oscillating charges will produce an electromagnetic wave. So suppose you have an electric field going up and down. Let's call it the y-axis. Okay, that's the y-axis going up, the x-axis across. It's going up and down. And you have a magnetic field. So that's E, the electric field in red. And the magnetic field is going across, back and forth. Back and forth. B, let's call that the x-axis. So an oscillating charge produces an electric field, which then produces a magnetic field, which then produces an electric field, ad infinitum. Okay, forever basically. So therefore, an electromagnetic wave is a self-propagating wave. Okay, so continuous oscillation gives you a continuous electromagnetic wave. And so to summarize, Maxwell developed 4 equations to unify electricity and magnetism, and he introduced the idea of electric and magnetic fields, made a modification to Ampere's law by adding this additional term here, showing that electric fields can also give rise to magnetic fields. And with those 4 equations, he was able to show that light is an electromagnetic wave, and all electromagnetic waves travel at the speed of light. And they're self-propagating waves.